Good afternoon, ladies and gentlemen, and I'm Colonel Venkat, Director AICT New Delhi, and it gives us immense pleasure to welcome one of our most esteemed panelists and esteemed speakers, Dr. Unnikrishnan PC from Rajagiri School of Engineering and Technology, Cochin. Dr. Unnikrishnan, sir, a very warm welcome to you, sir.
Thank you, madam.
Thank you, sir. It's an absolute pleasure and an honor to be listening from you. And as part of our continuous quality initiatives to enable our faculty members and to ensure that our faculty members all across the AICT approved institutes do continuously upgrade themselves as far as their professionalism is concerned and as far as their knowledge is concerned, we try to get the best in the fields to have a conversation and a one-to-one audience with our faculty members, and after that we give our full open option for people to put up certain bit of query recommendations. So towards that, on behalf of Chairman, Honorable Chairman Sir, Vice Chairman Sir, and the Member Secretary, we warmly welcome Professor PC Unnikrishnan Sir. And just to give a small introduction about Sir, because if I start speaking, it runs into pages and pages. Sir is highly qualified as far as academics is concerned, with having done all his qualifications. His experience is capable enough that he has been specifically and personally chosen to give a talk on this subject. And the subject per se also happens to be one of the most reputed and sought after subjects. And I can only request one thing, sir. AICT is honored to be having you on board in today's talk. We would request each and every attendee and participants who have logged in to very carefully be listening on talk on distributed generation and smart grids. It would be our pleasure if at the end of the talk, in the chat box, you could write down your comments and all, and we would then request without troubling Unnikrishnan sir, if it's convenient to you, we will take it on there only, sir. Otherwise, we will compile it and have it sent to you for your comfortable viewing it later and responding back to the participants, sir. Ladies and gentlemen, it's my honor now to hand over the platform and screen to Dr. Unnikrishnan sir. Sir, Unnikrishnan sir's platform is all yours, sir.
Thank you very much. I hope my presentation is visible to you.
Absolutely, sir. Very much. You are audible and presentation visible clearly, sir.
Okay, thank you very much. I wish to thank the AICT officials and also my friend and colleague, Mr. MP Punia, for giving me an opportunity to talk on behalf of Rajagiri School of Engineering and Technology. This webinar is on distributed generation and smart grids. I am given around 2 hours, so I wish to complete my slides within that time. So with that, we start the topic. I am Dr. Unnikrishnan PC, professor in Rajagiri School of Engineering and Technology, Electrical and Electronics Engineering Department. And with this quote from Mahatma Gandhi, we start the presentation. So through my slides, we will understand what is distributed generation, why we need distributed generation, what is wrong with our current electrical grid, a little bit of the evolution of the electrical grid. Then we will see what is a smart grid and why we need smart grids. And we will see a pilot project on smart grid also. So my presentation is divided into 8 sections. We will see each one of this session one by one. So the first one is the population growth. You can see the world population from 1,700 to 2,100 here, and roughly the current population is around 7.7 billion, and it will touch around 11 billion by 2100. So let us say by 2050 it will be touching around 9.7 billion. So the population is growing, and similarly our energy requirement is also growing. So if you, this is a world population forecast from 2020 to 2050, you can see the population has gone from 7.7 billion to by 2050, it will touch almost 9.7 billion. This shows the population is growing. And coming to our Indian population, our population was just 451 million in 1960, whereas it is now 1.3 billion by 2020. And the forecast says that by 2050, it will touch 1.6 billion. So the Indian population is growing very fast, and so as our energy requirement. So coming to the second part of my presentation, that is disruptive technology. We should understand what are the different disruptive technologies before we come to smart grids. So you can see here in 1998, the Kodak company employed around 170,000 employees globally. And in 2000, the digital photography pushed them out of the market. So a lot of employees lost their job. So this is something called disruptive technology. Let us stroll down the memory lane, Fifth Avenue, New York, 1900. So you can see a lot of hose carts. The question is, can you spot a car? Very difficult. The street is crowded with hose carts. But if you closely look at this picture, you can see one car over there. So now let us move to the same street in 1913, that is around 13 years later. The street is crowded with motor cars. And the question is, where is the hose or where is the hose cart? You cannot, very difficult to identify a hose cart. But if you closely look, you can see a hose cart over there. So in 13 years, something strange happened. Something disruptive happened. So a disruption happens when a new product or service helps create a new market and significantly weaken, transform, destroy an existing product. Or it can be a market, or it can be an industry. You have seen the picture on the right side, which is a mechanical typewriter. This has been replaced by the PCs, personal computers. Similarly, Walkman was replaced by iPods. And our batteries, current batteries, will be soon replaced by nuclear batteries, which has a lifespan of maybe more than 100 years. So even if you throw the mobile, you will take out the battery. So this is a transition, or you can see all a typewriting machine, a black and white television, a telephone, all these were there before 30 years in some of the houses or most of the houses, which were slowly replaced by electronic typewriters, color televisions, mobiles, then tape recorder and radio clubbed into two-in-ones. And all of them were later converted into computer. You can do everything, all these functions in a desktop computer, which was replaced by a laptop. And now everything is in your pocket as a mobile. And this mobile can do much more than what you can do with all these things. So this is a list of a few disruptive technologies, which we will see, and we will concentrate on few of them. So the mobile internet, the automation of knowledge, Internet of Things, cloud technology, autonomous vehicles, next generation genomics, energy storage, 3D printing, advanced materials, renewable energy. These are some of the, I have just listed 12 disruptive technologies. Why 12? We will come to that soon. So the first one is the artificial intelligence. So this is going to revolutionize the world. You will see a lot of applications of AI in almost all fields of all walks of life. Second one is the mobile internet. In 1980s, we used the internet just for a net connection. In 1990s, we started using it for e-commerce. Then later, the mobile came, and then the cloud application came. And right now we are using it as sensors. And in future, by 2030, we will be using our mobiles as actuators. It means you will be actuating many of your equipments like car, home appliances, and many other things just by using your mobile phone. The third revolution is, the disruption is of IoT, Internet of Things. So by Internet of Things, you can connect almost all equipments, all cameras, all devices all over the world, and it can be connected to Internet, and you can either monitor it or you can use it for control purposes. So this is one of the top disruptions. Then the application of IoT in home and automation. So IoT, this is one of the applications of IoT. Soon all the home appliances will be having some ID which will be connected to a remote device, maybe like a mobile. And using IoT, you will be able to control all of them remotely. Then application of IoT in smart grids. So what is a smart grid and how IoT is used in smart grids, we will come in the last part of my lecture. Space colonization. So people now are thinking about moving to the space and make colonies over there. So this is also a disruptive technology. 3D printing, it's something like you have a imaginary car in your mind and you go to a printer, a computer connected to the printer, and you give your specifications to the computer, and the printer will print out a car and you can just drive that car home. So even though it is very imaginative right now, many applications are already done in such printers. Medical innovations, you can change the genes, you can change the chromosomes, many diseases will vanish, it will increase our life expectancy. So many things are there in disruptive in medical innovations. High-speed travel, people always want to travel very fast. So high-speed travel is an area of disruption. Then robotics. Robotics has wide applications. I will not be surprised in another 2 years' time, most of the shops around you will be either vending machines or robots will start packing food items for you. Blockchain technology. This is also a top disruptive technology. Autonomous vehicles. Autonomous vehicles means driverless cars, driverless drones, swam boats. They will be widely used to supply items. They will be used like taxis. So a lot of disruptive technology here too. So this is a news article dated January 6, 2020. Waymo's autonomous cars have driven 20 million miles on public roads. So already they had started testing autonomous cars. Advanced virtual reality. This is also a hot area, a top disruptive technology. So this is something like I am talking to you in English sitting in Cochin. My image, my voice, it can be transmitted maybe to Japan, and a holographic projection in Japan can be in front of the Japanese students. I will be talking to them in Japanese language. The 12th one is the renewable energy. So I stop with the 12th one because I want to concentrate on the renewable energy, which is going to affect the distributed generation, and we will be using renewable energy sources in smart grids. So what are the different renewable energy sources? I have taken 4 or 5 here: the solar energy, the wave energy, the electrochemical energy, geothermal energy, wind energy. These are all in general we call the renewable energy, out of which extracting energy from waves, from tides, from geothermal, electrochemical, all are a bit difficult. The easier ones are the solar and wind. So there is a lot of scope in solar energy and wind energy in India. So this is a Tesla smart home. This is a picture of a Tesla smart home. What you see here is the rooftops are made up of solar panels, which will generate electrical energy. And what you see as walls are power packs. So the generated energy will be basically stored in those walls. And this energy will be used for your daily purpose, your electrical vehicles, and so on. This is a news article dated 30 December 2019. Okay, so the Tesla Model S long range is already on the roads. It can go 603 kilometers in a single charge. The only problem is the cost. It is a little expensive, around 70 lakhs right now. This is another news article from Bill Gates. So he says that EVs are the future of autonomous automobile industry. Only the price is a little high. This should come down. Then clean disruption in transportation. In future, we will stop using coal and petroleum products. Why not go for renewable energy sources, which are clean? So we will be charging our cars from renewable sources like wind or solar. Why go for electric vehicles? If you take a normal gasoline car, there are more than 2,000 plus moving parts. Whereas if you take an electric car, the number of moving parts are 100 times less. So the maintenance is less, the problems of even the cost will be less over a long time. This is a typical charging station. I have taken this picture from a website of China. This is a charging station in China. So this is another news article saying that the Tata Power will establish many charging stations by 2020, that is last year. And what is the progress? Yes, they had already, there are already 1,800 charging stations in India as on March 2021. And approximately there are 16,200 electrical vehicles en route. This is a news article which says New Bombay has recently opened the largest electric vehicle charging stations with 21 chargers. This news is from the website of the Ministry of New and Renewable Energy. India is able to get a record low solar tariff of rupees 2.44 per unit in Badla, Rajasthan. So it's a major disruption. So it will drive out all the petroleum products soon. This news article is dated December 2018. And I saw another news article dated December 21, 2020. You can see the NTPC, Aditya Birla and other two companies quoting rupees 1.99 per kilowatt hour or per unit. So the energy cost, solar tariff in India is hitting a record low of 1.99 rupees per kilowatt hour. Now going to the wind disruption. Wind also we are able to hit a record wind tariff of rupees 2.44 plus per kilowatt hour or per unit. If you look back to 2000, the windmills were of size 1.6 megawatt each, whereas by 2030, even now they are in the testing phases. By 2030, we will be having large windmills, which can, with a single windmill producing 11 megawatt. The height will be almost 125 meters. You should remember that the Statue of Liberty is just 93 meters. And the radius of the fan will be around 190 meters. So such huge windmills are going to revolutionize this world. So one windmill, 11 megawatt, if you install is 20 or 30 in a line, so you can get rid of all our energy problems. This picture I got from the internet. The ancient resource meets the 21st century. An old windmill and a new windmill in a single frame. So the world is going for 100% solar by 2030. That is the target. Okay, by 2030, the solar installations will reach to that extent that 100% we will go for solar. Now, the wind energy target for India right now by MNRE is 175 gigawatt till 2022. That is next year. By 2022, we should reach a target of 175 gigawatts. Now, the countries which are leading the or they are going for 100% renewable energy, you can see it is listed 1 to 11. I have highlighted Kenya because Kenya is an African country. Even Kenya is going for 100% renewable energy, whereas India is nowhere there. So it is our duty to push India into this list. So currently India is producing around 95 gigawatts. And by next year, our target is 175 gigawatts. So summarizing the top disruptive technologies, I have listed 12 here, out of which our interest is towards renewable energy, Internet of Things, a little bit of mobile internet, artificial intelligence, etc. Okay, so our stress is on renewable energy. So Odisha is setting up 2,200 megawatts of solar and 500 megawatts of non-solar renewable projects by 2022. So such large solar and non-solar projects are coming up. This is the India's largest solar floating solar power plant. This is in Kerala. It is maintained by KSEV. So now moving to the growing energy needs, that is the third part of my topic. So we will straight go to the National Power Portal and see our power generation. So don't go for all these numbers, just see the last number here. So this is in megawatts. So all over India, we are producing around 384 gigawatts. Okay, so that number 384 gigawatts, that is what we are generating right now. And out of which, by next year, we should have 175 gigawatt from renewable energy. That is our target. This is again the same table, splitted region-wise. And you can see the maximum electrical energy is generated by the western sector or western region, which is around 137 gigawatts. So the total generation in India is around 384 gigawatts. Now, energy is a commodity which can be exchanged, or it can be purchased, or it can be sold by using power exchanges. So this is a list of power exchanges all over the world. You can see the power exchange in Australia is called Independent Market Operator. France, it is IPEX Spot. Germany, European Energy Exchange. And in India, we call it the Indian Energy Exchange, or PXIL, Power Exchange India Limited. So these are some more power exchanges around the world. So if you go to the website of IEX, which is the Indian Energy Exchange, you can see the latest, you can see this picture I had captured yesterday. You can see on the right side the DAM prices. DAM stands for Day Ahead Market. DAM prices for 29th, that is today. So you can see the average market clearing price, the peak MCP, non-peak MCP, maximum MCP, all these things you can see here. And you can bid and buy electrical energy through these markets. This is another Indian electricity market, PXIL. Here also the function is almost the same. This picture has been taken from the website of vidyutpravah.in, and I have taken it at 6:30 yesterday, 28 July 2021, between 6:30 and 6:45. At that time, the price of electricity is 2.65 rupees per unit. So that is the price at that particular time. The price keeps changing every 15 minutes. So in the summer, the price will go up to 3 rupees, 3.5 rupees, maybe 4 rupees also. It may come down to 1.9, 2 rupees, etc. And you can buy power at this rate from the power exchanges. Remember, this is the cost of energy which the electricity boards sell you for 7 rupees or 8 rupees or even more. This is the website of the Central Electricity Authority, which controls all the electrical power system activities, and also it controls the exchanges. Everything comes under the Central Electricity Authority. Now, let us look at the load requirement or the load growth. If you look at the International Renewable Energy Agency's report, by 2050, you can see the rightmost bar chart. In 2016, the total installed power capacity was around 6,000 gigawatt, which is going to grow to 20,000 by 2050. So around from 16 to 20,000, 6,000 to 20,000. So it means the installed power capacity will almost triple by 2050. So that is how the load is growing. So the India's installed power generating capacity right now, we had seen it earlier, it is 384.1 gigawatt. This is as on June 2021. And it is the third largest in the world. The first one being the China and the second is the US. If you look at the load growth, our load is consistently increasing. One thing is because of our population. You can see in 2012, the load was nearly 120 gigawatt, whereas by 31, 32, it's going to cross 500 gigawatt, or by 2050, it will touch 600 gigawatt. So this means now we are producing around 384 gigawatts. In another 10, 20 years, it's going to double. Okay, in 20 years time, our load will be double. So we have to increase our generating capacity also. We have to increase accordingly. That means we have to make our generating capacity by about 600 gigawatt by 2050. Now we will come to the fourth part, which is the sustainability part. So all of you are aware about the sustainability. The industrialization has led to the increase of the average climatic conditions. That is, the average temperature has already increased by 1.65. And if this 1.65 increase remains, then in few years, most of the glaciers, northern and southern glaciers, will melt, which will cause havoc all over the world. The sea level will rise, and most of our coastal cities will go underwater. So sustainability, we have to somehow cut down the increase in average increase in the global temperature, and that is only possible by reducing the use of non-renewable energy sources, that is coal, petrol, all these things we have to stop using. So we have to go for sustainable habitat. We have to go for zero carbon emission techniques, building sustainable transport. We have to go for sustainable cities. We have to go for energy efficient buildings. So even waste management, or we have to produce zero waste, then only we will be able to, the human beings will be able to survive in this world. So this is one example of a zero carbon building in Hong Kong. It produces enough energy for its needs. So you can see a lot of solar panels over there, and these solar panels produce enough energy for that building. This is another example of a net zero neutral airport, which is nothing but the Cochin International Airport Limited. The CIAL is producing around 1.6 lakh units every day. So the excess energy is fed to the grid, and whenever they need it, they take it back. So it is a zero carbon airport. Now coming to the fifth part, which is the distributed generation. So what is distributed generation, and why we do need distributed generations? So distributed generation or distributed generators are small, modular, decentralized. It may be grid connected or it may not be grid connected energy sources, which are located very near to the place where the energy is used. That is the most important part. These distributed generation sources are near to the load. So when the generator is near to the load, the transmission and distribution losses are get rid of. That is the main advantage. And most of them are renewable based energy sources. So either it is a solar based, or it is a wind based, or tidal, or other types of renewable based. So various DG technologies are available. I will just scan through it. I will not explain them. The first one is micro-turbines. So they are 25 to 500 kilowatt turbines. The size of such turbines is roughly like your fridge. Then gas turbines. Thirdly, fuel cells. A lot of vehicles are coming out these days with fuel cells. This is an example. ISRO and Tata Motors, they developed India's first fuel cell bus. This is a news article dated 2018. So such vehicles are already on the load. They combine hydrogen and oxygen. The fuel cell produce electricity, and the byproducts are heat and water. Then solar energy, wind turbines, bioenergy and fuels. So biomass is any organic material which has stored sunlight in the form of chemical energy. So this can be converted into electrical energy or heat energy. Then combined heat and power system, Stirling engines. So a Stirling engine is just a heat engine that is operated by a cyclic compression and expansion of air. You can see a solar Stirling engine on the right side. You can see a reflector which will reflect the sunlight or the radiation of sun to the input of the Stirling engine, and the Stirling engine will produce electrical energy. Marine and hydro power, we can have small hydro, or we can say mini hydro power generation. We can extract energy from tides. We can also extract energy from waves. All these are possible, but extracting from waves and tides have their own limitations. The main problem with most of the renewable energy sources are they are intermittent and non-dispatchable. These are the two main drawbacks. I mean, you cannot say it is available all the time. For example, solar is not available during night. wind, when the wind velocities are less, the wind energy is not available. So we call it intermittent. They are not continuous. Similarly, they cannot be dispatched. So that is a critical problem in electrical engineering, load dispatching. Geothermal energy. This is another source of energy. Now the advantages of distributed generation is, the first one is it's clean energy. It reduces the thermal pollution, reduces the transmission and distribution losses, offers fuel diversity. And another major advantage is if you have a lot of distributed generators all around you, all of them can be combined into a microgrid, which we will see after 2 slides. Now, integration of distributed generators to grid, this is also important, because whenever you have a set of solar panels at your home, if you produce excess energy, you can feed it to the grid. And similarly, when there is no solar energy, that is during the night, you can get energy from the grid. So interconnection of distributed generators with the grid is important. So this will basically optimize the electricity infrastructure. And the whole thing will become less centralized and more consumer interactive. So consumer will be more concerned with whatever infrastructure available at his premises. It will also facilitate market interaction. I mean, if you are producing excess, you can sell it to the grid. KCB will buy it. So market interaction, you can sell it to other parties that we will come at a later stage. And the energy efficiency. Now moving on to the microgrids, which is the 6th part. So what is a microgrid? So you can assume a microgrid as a cluster of loads and micro sources operating as a single controllable system that provides power to its local area. So if you look at a microgrid, there will be a lot of loads, there are a lot of micro sources. All this will be connected together, and there will be a central controller controlling all these things. There will be energy storage also. So such a cluster of loads, micro sources, energy storage devices, and they should be controllable, and it should provide power to a local area. Such a concept is called a microgrid. So this microgrid, normally they operate in synchronization with the grid. I mean, the whole of the microgrid can be connected to the grid, and that connecting point is called the PCC, or the point of common coupling. So the microgrid can support the grid, and also when there is a need in the microgrid, the grid can support the microgrid also. So microgrids mostly operate in synchronization with the utility grid. Microgrids are a complete solution for rural electrification. It is impossible to take electrical transmission lines to deep into the forests, deep into the deserts, to mountains. It's almost impossible. Whereas we can build microgrids and solve the rural electrification problems. So wherever the tribal villages deep inside the forest and all, we can have a microgrid using maybe solar, using wind, and also to support them, we can have diesel generators also, and we can build a microgrid in rural areas where tribals live deep inside the deserts, deep inside the forests. So microgrids are complete solution for rural electrification. Why we need microgrid? Already this is answered. It's a reliable source of power, clean, the operation and investment problems, resilience. If there is a natural calamity, you can bring power faster, that is resilience. It's green power. It will complement the main grid. Slowly we have to get rid of the grid. Each and every house households should produce enough energy for their needs. It will improve the power quality and it is enhances social well-being, that is the rural electrification, and the consumers can participate in the market, that is we can sell our excess energy to the market. So this is a line diagram of a microgrid. You can see at the bottom DG1, DG2, DG3, DGN, etc., etc. So each distributed generator may be solar, maybe wind, or maybe something else. So mostly we deal with solar and wind. Each distributed generator will have a controller, and we will call it a micro source controller. So this micro source controller can control the inverters. So by changing the inverter settings, it can change the voltage, change its voltage profile and frequencies locally. So every distributed generator, you will find a controller, and you will find a central controller which will be controlling, or basically it will be giving set points, voltage and frequency set points to each and every distributed generators. So you can see all the distributed generators, they are connected to a common AC bus. Why AC bus? Because our loads are AC. Now remember, each distributed generator, some might be solar, some might be wind. So a solar produces DC, a wind produces AC. So whatever it produces, whether it produces AC or DC, it has to be converted into DC. Why? Because we want to store it using a battery. So a battery is used to store excess energy. So a battery stores energy in DC form. So whether the distributed generator which produces DC or AC, it has to be converted into DC and then again inverted to AC and connected to the common AC bus. So this is the whole idea. Now the central controller has control over each and every micro source controllers, and also it can open and close the STS, that is the static switch, which connects the grid to the main grid. So the main grid is connected to the microgrid at the PCC through a static transfer switch STS. Okay, maybe in future all the loads will be DC, so this conversion of DC to AC may be get rid of. Especially in rural electrification, we don't convert it into AC because all the loads, we will have DC bulbs, DC fans, DC televisions. So when everything is DC, no need to convert it into AC. So in rural electrification, we use DC microgrids. So once again, microgrid configuration, microgrids can be classified into AC microgrid or DC microgrid. So in AC microgrid, we will have AC at the point of common coupling. Whereas in a DC microgrid, we will have DC at the point of common coupling. And if you want to convert it into or connect it into the grid, you have to change this DC to AC and synchronize. This is another picture of the central controller connected with all the renewable energy sources through RS-485 serial communication links, and it can also send signals to the PCC to connect or disconnect the PCC using a static transfer switch. Now the microgrids, they have three modes of operation. They might be connected with the grid, that is called grid connected mode. So in the grid connected mode, microgrid is just an extension of the utility grid. Power flows from the utility and it is optionally consumed. If you want to consume it, consume it. Otherwise, don't consume it. Another mode is the disconnected or islanding mode. When a microgrid is disconnected from the utility grid, it is called the microgrid is in the islanding mode. Okay, this islanding happens because of some faults in the grid or maybe some faults in the microgrid. So once it is disconnected, then you have to reconnect it. Reconnecting means you have to go through the process of synchronization. I hope electrical engineers knows the process of synchronization. We have to see the voltage, phase and frequency profiles and synchronize them. In addition to voltage, frequency and phase, we have to see the phase sequence, and also in this type of synchronization, we have to see the harmonic content also, because in microgrids we use a lot of power electronic equipments, converters. So this will introduce a large quantity of harmonics. So these harmonics will create a problem while synchronization. So each and every local electrical authority specify certain restriction, or they restrict certain levels of harmonics. Only if the harmonic level is lesser than that, they will allow you to synchronize. The third mode is the standalone or isolated mode. This you will find in rural electrification. Microgrids are not at all connected to the grid. All microgrids which are at remote locations are standalone microgrids. So we will skip this slide. So whenever there is an abnormal condition in the grid, or it may be in the microgrid, so the static transfer switch will be disconnected and the microgrid will go into an islanding mode. Now, when the microgrid is connected to the grid, microgrid has nothing to do because the grid will take care of everything. So microgrid is just a load. Whereas when the microgrid is in the islanding mode, the microgrid has to take care of the all the activities within the microgrid. It has to monitor the generation, it has to monitor the load, and at any point of time, there should be a power balance, that the generation and the load should be equal. So we call it load dispatching. So also there will be voltage and frequency fluctuations when it is suddenly disconnected. So the central controller has to take care of, or the microgrid has to take care of the voltage and frequency management. It has to see the balance between the supply and demand. It has to maintain the power quality. Then micro source issues, it has to be solved because some micro sources will be intermittent. They may not be able to produce energy. So in that case, they will not be able to share the load. So other micro sources has to share excess load. So the central controller has to manage the balance between the supply and the demand. Then it has to maintain the communication among all the microgrid components. So microgrid components means the distributed energy sources, the load, and the energy storing devices. So all the operation of the microgrid is done by the MCC or central controller. Micro source controller, this is the controller which is attached to each and every distributed generator. So micro source controller, it controls the voltage profile at the load end and power flow of the micro source independently. So micro source controller will be connected with the central controller. So the micro source controller should ensure that it supplies its share in the standalone mode. So whenever there is an islanding, the central controller will ask a specific micro source to generate certain amount of energy, and the micro source controller should see that this energy is supplied. So there is a coordination between the central controller and the micro source controller in balancing the generation and the demand. The central controller, it looks after the overall control, it maintains the power quality. There are two modules within the central controller. One is the energy management module, EMM, and second is the protection coordination module. The energy management module, it provides voltage frequency set points to the micro source controllers. Also, it provides active and reactive power requirement for each micro source controllers. So the micro source controller should see that the frequency and the voltages are maintained as decided by the energy management module. Secondly, the protection control coordination module. So it looks after the faults in the grid, loss of grid, disconnecting the grid, resynchronizing the grid with the utility, etc. Now comes the interconnection of microgrids. So when you have two microgrids nearby, you can interconnect them. Firstly, why we should interconnect? That is the first question. So if you interconnect many microgrids, you will be able to meet large loads. So such interconnected microgrids, in general, we call it as a power park. So why interconnect microgrids? As per the IEEE regulations, the maximum capability of a microgrid is restricted to less than 10 MVA. So if the load is more than 10 MVA, one microgrid cannot cater the needs. So in that case, we have to connect several microgrids to cater to the needs of the large load pockets. So these microgrids can be interconnected through a common distribution network, or it can be the utility network itself. Now, remember, each microgrid will have its own central controller, which will execute its control in coordination with the central controllers of the nearby microgrids. So the basic advantage is whenever you have access and somebody else has less generation, you can share your resources. That is the basic. So you can cater to higher load pockets by interconnecting the microgrids. So interconnected microgrids has greater stability, greater controllability, and with a distributed control architecture. And redundancy. If some distributed generators fail, we can always get energy from the nearby microgrids. And also the individual microgrids have to handle a limited energy. So the distributed generators can relax for some time. Now coming to the seventh part, which is the introduction to smart meters and intelligent electronic devices. Let me take a glass of water. Sorry. So in this section, we will see the need of smart meters, and we will see intelligent electronic devices. I think all of you might have seen a traditional energy meter. It looks like this. It's an electromechanical meter with a disc rotating, and the number of revolutions per minute or per second can be converted into energy. These meters are slowly replaced by digital energy meters. So these type of meters are commonly found in households these days. Now slowly all these meters will be replaced by smart energy meter. So in India right now, energy metering and billing, we use electromechanical, and sometimes we are using digital energy meters also. So it consumes more time and labor. The meter reader has to go behind all the consumers, and if the house is locked, there is a problem. If there are dogs, there is a problem. So it consumes more time and more labor. So the traditional billing system is inaccurate. It is slow, costly, not flexible, and not at all reliable. So accuracy in billing is highly recommended. It will avoid a conflict between the consumer and the utility. So smart energy meter give real power consumption accurate billing, real-time monitoring, less time consuming and cost effective. So this is a picture of a conventional metering and a smart metering. So in a conventional metering, a man has to come to the load or come to the consumer, and then he has to note it down or then take it to the utility database. Whereas in smart metering, everything is automatic. There will be smart meters. Inside the smart meter, there will be a SIM card, and every smart meter will be having a SIM card, and the database can directly access the power from each plugin. Excuse me, 1 minute. Plugin or power is on. Just a minute, hold on. Power is on, yes. Okay, the parts. The parts of a smart meter are signal acquisition, signal conditioning, A to D converters. Just hold on, there is some power problem here. It is coming, I think. Okay, thank you. So different parts of a smart meter are the signal acquisition part, signal conditioning part, then the A to D converter part, the computation part, and finally the communication part. So as usual, the signal acquisition, we take the voltage, frequency, current, then we calculate the power factor, active and reactive power, and THD, etc. And there is a signal conditioning part which can do the addition, subtraction, attenuation, all those things. A to D converter can convert into digitals, analog to digital converter. And finally, the computation part and the communication part through wireless option or PSTN options or even power line carrier communications. So normally we calculate the units of a month, bill of a month, real power, load on a line, last unit details. These are the common things which we calculate from the meter. But in a smart meter, additionally, we can have different tariff options, demand response. The demand response means we can have flexible tariff. I mean, the tariff will not be constant all the time. When the loads are larger, the cost will be higher. For example, from evening 7 to 10, when everyone turns on their lights and fans, the load will be high. At that time, you might have to pay higher. So what you will do is basically you will be forced to shift your, like washing and all, you have to shift from that timing to some other time where the rates are low. Then there can be smart thermostats. So you can remotely control your applications through a smart meter. So sitting at my office, I can turn on the water heater, I can turn on some geysers or washing machine, I can remotely turn on. So smart meters are gateways for remote access of devices. You can have a prepaid metering just like mobile phone. We can recharge the mobile for 500 rupees, and once 500 rupees is over, the mobile will be disconnected. Similarly, you can have smart meters which are prepaid. So you can decide, okay, this month I will spend rupees 500 on my electricity usage. So once your prepaid amount is over, your connection will be disconnected. So it will enable better grid monitoring, remote connecting and disconnecting of users. Appliances can be remotely controlled. So all these things are possible using a smart meter. So we will skip this slide. All these things we have already seen. Now the disadvantages is just because smart meters make use of a telecommunication line. So the consumer has to pay for the telecommunication charges also. And if the telecommunication line is disconnected, there may be some problems. Now coming to home area network, all the equipments in your home can be connected to a network, and such a network is called a home area network. So I will skip this. It may be wired or wireless. Different technology standards are available, Zigbee and all. Then from home area network, we come to NAN, neighboring area network. It's basically, it allows smart grid infrastructure to connect smartphones, smart meters and distributed automation equipment to wide area network. So it is a network between the WAN and the HAN. Okay, so NAN is something between the home area network and the WAN. So from HAN, we can go to WAN and then to NAN and then go to WAN. So there is a network within the house, which we call a home area network. Outside the house, we have NAN, and the smart meters through NAN can be connected to the utility using WAN. So a wide area network is just like internet. It's a network that covers a large geographical area. So it spans a large geographical area. There are different types: point-to-point technology, circuit switch technology, packet switch technology, and so on. Now from smart meter, we come to advanced metering infrastructure. So advanced metering infrastructure is the complete infrastructure from smart meter to the utility database, all the communication network, the protocols, everything together is called the advanced metering infrastructure. When I say smart meter, it need not be always electricity meter. A smart meter may be a gas meter, or it may be water meter also. So this is a pictorial representation of how the data flows from the consumer to the utility. There are a lot of data collectors. So from the smart meters, the data will come to the data collectors, then it will go to the data concentrators, and through NAN and WAN, it goes to the utility database. So this is an overview of the automatic metering infrastructure. There are different layers: the consumer portal layer, metering layer, communication layer. So the consumers will be restricted only to the consumer portal layer. So each and everyone has his own access rights and permissions. Now moving to intelligent electronic devices. So this is a picture of how we acquire data from the relays and circuit breakers. So normally we get the following data, which is single phase currents, bus voltages, three-phase watts, T is three-phase watts, then trip status, whether it is closed or open, then the reclosure status. These are the data normally we get from the relays and circuit breakers. And remote terminal units, which are placed in substations, they are wired to the circuit breaker contacts in the substation switchyard. So we are talking about a traditional substation. So data is collected by RTUs located in substations. So they collect analog data obtained through connecting transducers and instrument transformers, that is CTs and PTs. And this data is given or fed to the SCADA systems, supervisory control and data acquisition systems. Now, what are the drawbacks of SCADA? That they are not very robust. It can bring some errors. Secondly, its scanning rate is very low. The rate of scanning is low. So when the scanning rate is low, it cannot track dynamic changes. Dynamic changes means changes which are happening within microseconds and milliseconds. So these limited SCADA capabilities can be overcome by using intelligent electronic devices, or in general we call IEDs. Basically, IEDs are microprocessor-based controllers of power system equipment, such as breakers, transformers, capacitor bank, etc. They have high scanning rate. So IEDs are installed in substations basically for automation in data collection, improving the data integration, monitoring, and control. Then data sampling synchronization is the major advantage of IEDs. That is, two IEDs located in different parts of a substation can be synchronized. So they'll be operating with the same clock. So you can have a local sampling synchronization, and also you can have a system-wide synchronization. That is, an IED located in Kerala or an IED located in one state and another state can be synchronized. They may be running with the same clock. So a system-wide synchronization is also possible by using IEDs. This is done by using or connecting IEDs to GPS receivers and satellites. And the sample data can be correlated between different substations. This correlation is possible only if we are using a common time reference, that is synchronization. So otherwise correlation is not possible. There are many types of IEDs, but I will mention only just three. One is the digital protective relay DPR, digital fault recorder DFR, and thirdly the circuit breaker monitor CBM. There are many other IEDs also. Now we move on to phasor measurement units and wide area measurement systems. So what is a phasor measurement unit? PMUs are basically, they are digital data recording devices that measure and export GPS synchronized. That is the most important thing. A PMU in one part of the country will be synchronized with another PMU in another part of the country. It means both of them have a common reference signal. That is very important. Then only once you have the common reference signal, then only you can find the phase difference. That is very important in electrical engineering. And their sampling rate is quite high, 6 to 48 samples per cycle. So you can have a dynamic measurements of phase voltages, phase angles, currents, frequency, etc. So it will slowly replace the traditional SCADA. These are two models from ABB and Microdyne. Now, before we move ahead, we should understand what causes power to flow in a grid. In DC, power flows from a high voltage point to a low voltage point. But in AC, the voltages are same everywhere. So how the power flows? So it is the power angle or the voltage angle. The power flows from a high voltage angle to a point of low voltage angle. So the phase of the voltages at different points is very important, and that is something which we have to measure. That only will be used in balancing the power. So you can see here two buses are shown, bus 1 and bus 2, and PMUs are installed at bus 1 and bus 2. Both the PMUs are using a reference signal, a common reference signal, which is represented by a black dotted line. And the signals blue and red corresponds to the PMU signals of bus 1 and bus 2. So with the reference signal, we can find how much is the voltage and voltage angle. So once you get the angle, you will be able to control the current flow. It's a comparison of SCADA with PMUs. SCADA measures analog signals, PMUs measure digital signals. The resolution is low 2 to 4 samples per second. PMUs with up to 100 samples per second are available. Observability, only steady state observability is possible with SCADA, whereas dynamic observability is possible with PMUs. So monitoring, only local monitoring is possible with SCADA, whereas a wide area monitoring is possible if we use PMUs. And there is no phase angle measurement in SCADA, whereas we have phase angle measurement in phasor measurement units. If you see this picture, you can see the time between 5.21 and 5.22. In the first picture, it is almost flat, but when you see from a PMU, you can see the oscillations. The first one is a picture from SCADA, data from a Kramer substation in California, whereas the second picture is from a PMU. So PMU can give the dynamic, very minute dynamic oscillations can be visualized by PMU outputs. So SCADA measurements cannot see most oscillations. So it can give misleading impressions, whereas synchro phasors are needed to observe oscillations because of faster data sampling, greater data resolution, and wide area. These are the parts of a phasor measuring unit. You can see the GPS receiver is connected to the satellites, and there are 24 satellites. So at any point of time, 3 satellites will be connected to the GPS receiver. So the signals which are sent from the PMU will be location and time stamped. So we get the phase angles, which are location stamped, which are time stamped. So there is an anti-aliasing filter. The GPS provides exact location. So 24 satellites orbiting in 6 geosynchronous orbits. So at any given instant, 3 satellites are visible in any point of the Earth's surface. So there is a phase lock oscillator. I will not go to the details here because I am already short of time, around 4:20. So there is an A to D converter. Now, this is another picture, a conceptual diagram of a power system using phasor measuring units. So you can see all PMUs are GPS synchronized using satellites, and there is a central controller which can be used to control all these things. So these are the advantages of PMUs: more number of samples, GPS time synchronized, and also the location is, each signal is time and position stamped. Wide area measurement system is basically a collective technology to monitor power system dynamics in real time, identify system stability related weakness, and helps to design and implement countermeasures. So basically, every part of the power system, we will be employing many PMUs, and all these PMU data will be coordinated and used for controlling. So a pictorial representation of VAMs is shown here. You can see large number of PMUs. So now we move to smart substation, and then only we can move to smart grid. So a substation is part of an electric generation, transmission, and distribution network. All of you have seen substations. We need substation for stepping up and stepping down voltages, and also due to a practical consideration of increasing the load, etc. These are the different parts of a substation. You will see power lines, transformers, switches, circuit breakers, CTs, VTs, and lightning arresters. And we move to the next part. There are different types of transformers, substations. You can see some substations are called transformer substation, used for stepping up and stepping down voltages, switching substations, PF correction substations, frequency changer substations, converting substation, especially to convert AC to DC used for traction. Now we come to a smart substation. What is a smart substation? A smart substation is a traditional substation plus IT support, the latest information technologies. So In smart substations, we use intelligent electronic devices, secondary devices, all protective relays, CTPTs, or we commonly call them as IEDs or intelligent electronic devices. Then TCP/IP instead of serial communication, and the application protocol of IEC 61850. That is the latest application protocol. And some substations use latest artificial and intelligent techniques for fast decision making. So most of the relays will be microprocessor based or intelligent devices. We'll skip this one also, skip this one also. So let us see what is IEC 61850 protocol. Here, the entire substation is divided into 3 layers: the process layer, the bay layer, and the station layer. You will see all the line protection devices, disturbance recording devices in the process level. You will see recorders and issuing of commands to the process level, etc., is done at the bay level. At the station level, higher functions are performed, like supervisory synchronization, etc., are performed in the station level. So this is again elaboration of the 3 levels: process level, bay level, station level. I will skip it. So the different components of a smart substation. One is the primary high voltage equipment, IEDs. Then the substation automation system, we call it SAS. It will be based on IEC 61850. Then protection devices, metering devices, time synchronization, the operation and maintenance. So almost all the operations will be automated. Then auxiliary systems such as video monitoring, fire alarms, etc., are called auxiliary systems. So substation automation is a very important part in. So there are different architectures: ring type, star type, hybrid substation. We can just see the pictures only. So here, this is one simple cascading type architecture is shown here. This is a redundant cascading type substation architecture, ring type substation architecture, star type substation architecture, and this is a hybrid type architecture. And with that, we move on to smart grid, which is the last part of my presentation. So what is smart grid and why we need smart grids? Some questions we had already answered before. You can see this picture. You can see factories, power plants, thermal power plants, hydraulic generation. So all these things are connected together to one grid. So it may be a vehicle, it may be so a lot of renewable energy sources, loads, factories, vehicles, they are connected together into one grid, and that is called a smart grid. So traditional power grid, all of you know, power flows in one direction only. The power flows from the generating station to the load. It goes through the substations and it reaches the consumer. The power flow is just one direction. The power cannot flow in the other direction. Whereas, so the problem with traditional power grid is one-way flow of electricity. The power generation is centralized, bulk generation, and we heavily depend on coal and oil, limited automation, limited situational awareness, and consumers lack data to manage energy usage. So consumers doesn't know anything. Now moving to a smart grid. What is a smart grid? A smart grid is a normal electrical grid plus the communication infrastructure. So along with the electrical grid, if you also have a communication infrastructure, then it becomes a smart grid. Now, what is the advantage? The advantage is a lot of renewable energy resources which are distributed at the consumer premises can be connected to the grid. So the power flow is now not in one direction. Power flow is two direction. Similarly, the information flow also is in two directions now. So two-way flow of electricity and information, that is smart grid. So what is smart grid? A smart grid is just a normal electrical grid. Along with we have the communication infrastructure. It will enable power flowing in both directions. So remember, power flowing in both directions is talking is easy. It will introduce a lot of security protection problems. So all this needs to be sorted out. So this is a definition of the smart grid. So it has three layers: the power and energy layer, the communication layer, and thirdly the IT or computer layer. So if we combine all the three, it will become a smart grid. So the 7 domains in smart grid are, if you see the bottom, you will see the generation, transmission, distribution, and consumer. They will be connected by a hard wire, or the energy should flow through these lines, which is shown by broken black lines. Whereas the markets, operations, and service providers, they are connected by information flow only. That is represented by the blue lines. Okay, so there is information flow and energy flow. The energy flow only in the 4 different domains, that is generation, transmission, distribution, and consumer. The other 3 are connected by information flow only. So why we need a smart grid? Electromechanical, electrical grids are inefficient, and they are highly prone to power failures. They are highly stressed also. The energy demand is increasing at a very fast rate. We have seen that by 2050, our load will be almost double. So with the increase in energy cost, customers also customer expectations are also increasing. It's not like before, customers are educated. So they also are bothered about sustainability. So they want to use green power. So all this is possible only if we go for renewable energy sources. So what way it will help us? So it will help interconnectivity of grids with various distributed energy resources. Online power exchange is possible. So whatever you produce excess can be sold to others who are in need of it. You can get better service from distribution companies, DISCOMs. Exploit DERs and efficient load control and a higher efficiency. Now, what are the challenges? The challenges are we have to increase the grid transmission capability, because when the load is high, definitely the current should go through these transmission lines. So the transmission capacity needs to be replaced or improved. We have to go for large number of offshore wind farms, floating solar power generations, energy storage devices. We have to develop decentralized architecture. We have to develop proper communication infrastructure, and most importantly, the consumer acceptance, educating the consumer. That is the need of the hour. So these are the various challenges. Then protection, etc. are also challenges. Initial cost, power quality, stability. When there are only 10 bulk generators, it is easy to balance the load and the power. When there are thousands of distributed generators and power flowing in both directions, balancing of load and generation is going to be a very big problem. We need better electric vehicles. Then we need political and economic frameworks and traditions. Standards need to be set up. We have to solve or create a legal framework, and the regulatory issues need to be solved. There are a lot of benefits of using smart grid. I will just skip through it. Now, finally, we move to the last segment, which is the Pondicherry Smart Grid Pilot Project. So these are some of the snapshots. It is developed jointly by the Power Grid and the Puducherry Electricity Department. About 60 collaborators are participating in the projects. The main objectives of the projects are indigenization of technology, a proof of concept in Indian conditions, knowledge sharing, capacity building, and development of scalable and replicable model, demonstrate the benefits to all stakeholders, and evolution of a commercial mechanisms. What is implemented is already AMI is implemented, PLM, peak load management, including the demand management and demand response is implemented. Outage management system is implemented. Some problem in power. So these are some of the things which are implemented. This is the single line diagram of the project. The grid control center has been established. Advanced metering structure is with around 1,600 smart meters, 29 DCUs. These are all installed. Various communication technologies are tested. Interoperable system implemented. AMI implemented. This is the outage management system which has been implemented. PQM, that the power quality management module is in place. Capacitor banks are switched automatically. Renewable energy integration with net metering is also done. Gross metering, net metering, all these things are done there. Peak load management, microgrids are there. So in general, this pilot project is successful. And street light automation, automatically the street lights will be turned on looking at the illumination. Energy storage devices and electrical vehicles with solar charging stations are implemented. Smart home energy management system is in place. And with that, I wind up my session. These are some of the references, and I have referred to a large number of internet resources. So thank you very much for patiently listening to this session. And once again, I thank AICT, the authorities of AICT, for giving me an opportunity. Thank you very much. If you have any questions, you can ask questions, or you can even you can contact me over my email ID. So thank you very much, sir. So if there are any questions, I will be happy to answer if I know the answer. Thank you very much. Yes, I have finished, sir. Is there any smart substation in India? Yes, there are a lot of smart substations in India. I had recently visited a smart substation in Tripunithura, Cochin itself. Fully automatic. Nobody is there. It is controlled from Madras. There are smart substations in India. Yes. And Schneider Electric Company is producing, they will just come with the substation and put it there. That's all. Everything will be in place. How can we use soft computing techniques in making the distribution of power smarter to make the rural regions, villages smarter? Yes, good question from Niranjan Kumar. Yes, we need to incorporate a lot of artificial intelligence techniques because up to 2013, all the grids were not connected. Now, all over India, we have one grid. So fast decision making has to be done in many situations. Otherwise, the entire grid will collapse due to some disturbance. So we have to use artificial intelligence, of course, soft computing techniques like neural networks, fuzzy logics, GIS, etc. come under, they are part of AI only. So a lot of AI is already being used, and there is a lot of research going on in how this can be used in power system stability. Thank you for the question, sir. Is the smart grid fully implemented in Puducherry or still in progress? This is a question from Ronald Lawrence. It is fully implemented, sir. It is operational. From Shantanu, is smart meter required continuous internet facility? If yes, there must be charges. No, smart meter does not need continuous internet facility. It can be, smart meter basically transmits the signals at some periodic time. So internet need not be there all the time. Only during specific periods of time, it should be available. Then only we can have continuous monitoring. Yes, there must be charges. Yes, internet charges will apply. That is one of the drawbacks with smart meters. Niranjan Kumar, sir, is the smart meters make use of IoT, and so we note them as smart? Yes, basically a smart meter is a meter which is connected to the internet by either Wi-Fi or by a line, so that it can continuously monitor the energy and transmit it to the utility, number one. Number two, it will have the utility can access the smart meter and disconnect non-priority loads. That I did not mention here. Actually, now the utility, if they disconnect a particular user, all his loads will be disconnected. Now, what is going to happen is with smart meters, we will have two types of loads, important loads and not important loads. So not important loads can be disconnected by utility. So utility will sign a contract with you when there is a need. Utility will disconnect the loads which are not important. Where will IEDs be installed? Is it in every part of the power system? IEDs are mostly installed in substations. It is basically to automate the fault recordings, basically it is connected with the circuit breakers, relays, etc. What standards needs to be followed for established smart grids? Standards are yet to be, standards are still not there. It has to be developed. Standards, legal frameworks, all this needs to be developed. Any scheme of the government which promotes non-conventional energy? Yes, there are incentives for renewable energy. You can install wind energy, solar energy, you will get incentives. Is IoT a part of smart grid? Yes, IoT is part of a smart grid. Without IoT, without communication and IT support, we cannot have a smart grid, because all these distributed generators, loads, the electrical vehicles, all this has to be connected. And all this is by using communication channels and IoT devices. Question from Dr. Jangam Shetty. Oh my God. I think I don't think I can answer to Jangam Shetty, sir. Thank you very much, sir. Enhancement of present grids into smart grid will cost more and difficult, because many of the equipments has to be replaced. Yes, you are correct, sir. So what we should do is, whenever a new connection comes, slowly, for example, if somebody asks for a connection for his house, install smart meter there instead of a digital meter, install a smart meter. So slowly we have to do, we cannot burden the consumer for shifting from our present lines to smart lines or smart grids. Any other questions, sir? I'm also new in this, and I think Dr. Jangam Shetty is a pioneer in this field. He too can support me. Thank you very much, sir. Any appreciation from you is highly valuable. Thank you very much. So if what are the recent technologies used for trading the energy for G2V and V2G? G2 grid to vehicle and vehicle to grid I have not covered in this part. The latest technologies I'm not aware, because implementing V2Gs is a real problem, because it will load the grid. So it is only, as I understand, of course, it is implemented in Puducherry, but when large number of vehicles will start charging from one place, I think the grid will be heavily loaded. So I think we have to develop some standards and all. From Shantanu, sir, due to smart meter, is there chance to increase our meter reading due to its accuracy and ability to capture small changes? No, sir. Due to smart meter, in fact, our bills will come down, because we will implement using smart meter. Basically, we will be implementing a flexible metering. I mean, the charges will not be constant at all time. The charges will be high during the peak time and charges will be low at the off-peak time. So you will postpone your non-priority activities like washing. Washing you need not do between 7 to 10 p.m. You can do it in the morning, where the charges will be less. So I think the charges will be reduced. And also you can have your own electricity generation and solve your energy needs. You need not depend on the grid. From Devendra, sir, how smart grid will be used to stop energy theft? See, in Puducherry, I have shown you, I have skipped the slides very fast. Already they had introduced a mechanism by which meter tampering can be detected. Okay, so when the meter tampering, the energy theft is normally done by tampering the meter. So that can be done. Then if somebody is directly taking energy from the electricity lines, of course, by the discrepancy between the actual energy usage and the actual energy generated is basically the transmission and distribution losses plus the energy theft. So very easily we can understand a theft is happening and we can identify the location, not exactly, but approximately. And by constant monitoring, we can catch the thieves. Niranjan Kumar sir, we have a comment saying that if downstream is properly maintained, upstream is benefited. Can we justify that with respect to our smarter distribution? If the downstream is properly maintained, upstream is benefited. Clearly, I don't understand what exactly you want to say. Can we justify that with respect to our smarter distribution? Basically, we are slowly going for every person should be generating energy for his needs. Over a period of time, I think this distribution grid and the utility may vanish. Like I am generating around 12 units every day. I consume around 7 to 8 units every day. So excess 3-4 units, I sell it to the state electricity board every day. And once in a year, they give me some small amount. So each one of us will be, over a period of time, will be generating energy for our needs. We mean downstream is load side and upstream is generation side. See here now, generation side, what you mean is the bulk generation. So now when the generation is distributed, generation is in downstream and as well as upstream. Generation is everywhere. Every house, there is a generation. After a few years, you will find solar panels in every house. So every house, there will be a generation. Of course, it will introduce a lot of synchronization problems. It will power balancing problems, etc. That slowly all these things will be taken care of. Thank you very much for the nice discussions. Thank you very much, sir. So if there are no more questions, I think we can wind up. The time is around 4:55. Sir, will the energy charges affordable to a common man in smart grid? See, the energy charges, I told you, 1 unit of energy right now, solar energy is costing around 2 rupees. Okay. And the utility is selling to the consumer for around 7 to 8 rupees. So if you are generating by yourself, so it is affordable, isn't it? Now the solar PV costs, so they are coming down drastically. Even I read that transparent PVs are coming. So with the decrease in the PV prices, I think energy costs will not increase. It will be affordable for everyone. You will be generating your own energy, basically. You will be connected to the grid only for exchange purpose. Surekha, Miss, thank you very much for the information. Thank you, madam. Thank you, sir. So if there are no more questions, I think we can. Thank you very much for all your compliments, comments, and happy to know that it was basically a surface treatment of the subject. We teach the subject in around 45 lectures. So packing 45 lectures to 2 hours, definitely there are a lot of information missing. Thank you, Mukherjee sir. Thank you, Shantanu sir. Thank you everyone for attending this session. Thank you. I will log out now. Thank you very much. I thank Mr. MP Punia and the ACT authorities for giving me this opportunity. Thank you very much.